Okay, so thank you very much, and thanks for inviting me to this great workshop. It would be interesting to give this after the game yesterday and after staying late, but we'll see. So this talk will be about incomplete phase transition at inflation, and it's based on this paper 203, 003. And this is work with Tomer Volansky, our student Yoel Barir, and Chen Sang, who's our postdoc. And let me start briefly with an introduction to several types of sources of gravitational waves, and essentially what can phase transitions do. So there's a very well-known story of phase transitions in the thermal Big Bang. So this is a Big Bang. And we know they source, if these phase transitions are strong first order, they source, they are driven by bubble nucleations. These bubbles collide and they source gravitational waves through several mechanisms. And we have a zoo of possible gravitational wave detectors for different frequencies. And so this is, I think yesterday Fabrizio mentioned this as well, but I'm going to just briefly go through this. So we have, here's omega gravitational waves, and here's the frequency. And we have it all the way from, let's say, 10⁻³ hertz, 10 hertz, and here's like 10⁻⁻12. So we have a huge range, and we have different experiments that probe different ranges. So we have, of course, all this region is excluded by CMB and essentially spectral distortions. Distortions. Here somewhere we have the PTA, I think 10⁻⁹, relatively. So this is pulsar timing experiments, and we have LISA here. So this is PTA. This is LISA. This is where LISA is going to be, and we have currently LIGO somewhere here. And of course, there are new experiments that are proposed for this entire range. And here we have already some exclusion, of course. And this was also mentioned by Fabrizio, that around the range of 10⁻⁶, all of this is excluded from anesthetic, so BBN and CMB. And this is where it stands. And of course, the frequency corresponds to when in the Big Bang the phase transition occurred. So LISA, for instance, is around the TeV range, slightly above. LIGO is even higher, and pulsar timing arrays is around the QCD range. And so here the frequency will just be corresponding to the redshift at which the phase transition occurred. So this is the regular story that is studied quite extensively in the literature.
So, sorry, can I ask you just the CMB goes all the way down?
Yeah, well, yeah, CMB goes all the way to around 10⁻⁻13 in this range, and even further here, you get the CMB perturbations themselves and B modes. But I'm not even going in that direction. I'm going to mention this later. I mean, at the end of the talk. Okay, so this is not what we're doing, but let me start with this. Now we can have phase transition. So we can have phase transitions after inflation, after reheating. We can have phase transition at inflation or reheating. So that's what I'm going to talk about. But of these, there's two sources of gravitational waves that they can produce. So let me start with the second one, which is not what we're doing as well. So here we of course know that inflation can produce gravitational waves. We already are familiar with this just from the Sitter fluctuations that produce gravitational waves through the just as basically with as a thermal production with the Sitter temperature. So here's inflationary phase transitions. but with a direct production. So here, let's talk about direct production of gravitational waves. So we know one story, which is the thermal story, but of course, if we have another source of gravitational waves, not just the de Sitter one, it's going to behave in a similar way. So here we can produce them from de Sitter fluctuations, or we can just produce them through dynamics. So phase transition, the main wall production, all of these stories, and similar, all of the things that could work here. So here, of course, I was talking about phase transitions, but similarly, this could be domain wall dynamics, anything that produces inhomogeneities. Similar, you can have the same story here, and they will produce directly gravitational waves that are going to freeze and are going to propagate to us today. And so the phase transition story of this was studied by Lian Tao and his group in this paper. And of course, there's many, many papers about the de Sitter fluctuations that I'm not going to mention. And this is, again, not what we are doing. So you can have a phase transition during inflation. It can produce gravitational waves through, let's say, bubble collisions. But and these gravitational waves will reach us directly from inflation until today. We are doing something.
Sorry, just a comment about this. So in this game that people are playing, my understanding is that they are always messing up, let's say, the late time phases of inflation. Otherwise, you will be screwed by CMB, no?
Right. And this is going to be a theme also for us.
Yeah.
So these phase transitions have to occur. Well, let me get to this, because I'm going to mention things that are going to be relevant for this as well. But yes, it has to be relatively late at inflation, otherwise you're screwing up the CMB, and this is also going to be true for us. Okay, so the third possibility is that inflation produces not gravitational waves, but rather scalar curvature perturbations. Okay, and so we have some dynamics, and we have inflationary production of curvature perturbations. So these are not tensor modes, but scalar modes. And of course, our whole intuition about scalar and tensor separation, the SVT decomposition, is based on the free theory. So once you have interactions, the modes are no longer separable. So at second order, you can produce out of these gravitational waves. So after inflation, these modes can produce secondary gravitational waves. So secondary just means that they're produced at second order.
Also during inflation, right?
Also during inflation, of course. So during inflation, it's sort of this. Yeah. So also during inflation, they can produce gravitational wave. But even after inflation, the modes survive and they can produce gravitational waves. Okay. So one example of this that is very, very well known is whenever you want to produce primordial black holes, you run into this story, this gravitational wave production. So, for instance, this can happen in these ultra slow roll phase. If there's an ultra slow roll phase, so the slower is the slower is the inflaton, the bigger are the perturbations, and comparable to the homogeneous part. And so if you have an ultra slow roll phase somewhere in your potential for the inflaton, so for instance, if your inflaton potential looks like this, where there's a flat region, so when the inflaton gets to this point, it will produce perturbations that are much stronger. So your spectrum will peak there. And at second order, you can produce gravitational waves, and of course, these perturbations can collapse and form primordial black holes. So we are going to focus on this story, but not on the ultra slow roll, phase, but rather on something quite different that I'm going to explain. Okay, so this is what we do. Okay, so let me start with this, and let me talk a little bit about the intuition for when these things are produced, what modes are produced, and how we should think of this. Okay, so here's some intuition for inflationary production of anything, of any inhomogeneity. Okay, so here's some intuition. So what's the story? We have a production of some mode of inhomogeneity during inflation, and then that mode freezes and it does nothing. Okay, it remains frozen until it re-enters back into the horizon after inflation ends. And once inflation ends, the Hubble sphere starts expanding again. So the Hubble sphere shrinks at inflation, the mode goes out of the horizon, inflation ends, Hubble sphere starts expanding again, and the mode re-enters back to the horizon, at which point it can do dynamics. And the dynamics it does, among many other things, is producing these gravitational waves. So really the way we should think about this story here, which frequency are we producing, has to do with when did this mode re-enter into the horizon, which is directly connected to when did this mode leave the horizon. So at which point during inflation did the mode leave the horizon? Okay, so let me explain this. So after inflation, the frequency or the size of the mode is set by the redshift at horizon reentry. And this corresponds to different redshifts for horizon reentry is so this corresponds to different time during inflation. Okay, so let me go back here. Okay, so early at inflation is this direction, late at inflation is this direction. Okay, so that the further, the later it is, the higher is the frequency because the modes are shorter, and the earlier at inflation, the longer modes exit the horizon, and so we get to lower frequency. Okay, so this is the important things. All the rest is details. Sorry. There we go. Okay. So let's talk about the idea. What's this? Okay, so what do we want to do? We want to have a phase transition in some hidden sector during inflation or in some spectator field during inflation that will produce these gravitational waves. And we especially focus on a regime that was not studied so far and was basically thought of as something that is bad for inflationary model building, which is phase conditions that don't complete. Okay, so let's talk about what happens. Okay, so here's our idea. Again, the most simple model we write for this is something like this. Okay, so here's the potential for some field. Okay, that during inflation starts somewhere here. Okay, so this is going to be related to what Diego asked, and the reason we don't start in the minimum is that we want some period of initial slow roll that will determine when at inflation does the phase transition happen. Okay, so the field starts somewhere here, it rolls to this point, and then it would transition here. Now, the tunneling can happen in different ways. This could be the regular vacuum tunneling, so Cosmology tunneling, or it can be tunneling due to de Sitter fluctuations, which is known as the Hawking-Moss instanton. And so let me just, for the purposes here, talk about Hawking-Moss, but almost none of the story changes if we talk about Cosmology. So you would have tunneling to this point, okay, and from this point they'll be rolling here, okay. Now for Cosmology instantons, this transition can be faster than Hubble, and so the transition can complete. But of course, it can also be in the regime where the gamma over V is less than Hubble to the 4th, and transition will not complete. But for Hawking-Moss, it never completes. Okay, so the transition, you have constant bubble production, but the number of bubbles that are being produced is less than what the universe expands. So most of the universe stays in the false vacuum here. Okay, now if you're worried about eternal inflation, let me just say this is not the inflaton. The energy here is subdominant, and after inflation, this transition will occur. And this is quite natural because you need to compare gamma over V to H, and as long as gamma over V is bigger than H to the 4 set by the vacuum energy here, there's no problem with eternal inflation. Okay, so if you're worried about that, this is what ensures this. Okay, so the reason why incomplete phase transitions are bad, in fact, this was the old inflation story, that of course, if this were to happen to the inflaton, inflation would never end. But this is not the case here, and we just use this to get an interesting pheno out of this, a regime that so far nobody really thought about. Okay, so again, we need to what do we need to do? We need to compare gamma over V, okay, the rate of transition per volume to Hubble to the 4th. Okay, and we're going to be in the regime where this is less. Okay, so this Hubble at inflation. But as I said, gamma over V is bigger than Hubble that is given by just this vacuum energy. Okay, so this is our story, and there are going to be some important parameters here. So let's call this delta n. So the delta n is how many e-folds at inflation does the field need to get here. Okay, now we have this, let me call this the V barrier. So this is the height of the barrier, and let me call this delta V. Okay, so this is our important parameters, and of course delta n has to do with the comparison between the mass of this the mass term of this field and Hubble. So the mass term of this field has to be slightly smaller than Hubble so that it doesn't reach the minimum directly, but rather takes a few e-folds of getting there. Okay, so let me first explain why do we need this? Why do we need this not to happen immediately, but rather we need to wait this while? And I'm gonna, at the end of the talk, I'm gonna mention the possibility where it does happen immediately and what we can do in that case as well. So here, what happens is if it were to happen immediately, suppose we just started here and started tunneling, then we're going to produce these gravitational waves. We're going to produce these modes that are going to produce gravitational waves that I'm going to talk about throughout inflation, from the beginning of inflation until the end of inflation. And we're just going to be completely excluded by the CMB part of the spectrum. Okay, so that's not what we want to do. We want to have a spectrum that is interesting for these pulsar timing arrays and the next range of gravitational wave detectors. Okay, so this is what we need. So let me connect this immediately already to the parameters. So for Hawking-Moss tunneling, we know that gamma over V is roughly equal to h to the 4 times e to the minus VB over h to the 4. So it's basically climbing the height of this barrier with a Hawking temperature of Hubble for a volume that is a Hubble sphere. So basically, what this represents is an entire Hubble sphere that suddenly jumped from this point to this point. So this is roughly 1 over Hubble, and it got into dB. Okay, whereas the rest of it is still in this false vacuum. Okay, so this is going to be the process. This process is going to happen with this probability every now and again. Okay, the probability is less than Hubble, so most of the volume does not go through this transition. Only some parts of the parameter space. This is going to produce some part of the space of inflation, and what this is going to produce is it's going to have a gravitational effect. Okay, that is going to produce a mode of inhomogeneity, which is basically the size of the bubble at when it was produced. Okay, that mode is going to freeze, re-enter the horizon, and produce gravitational waves at second order. Yeah.
Are you going to elaborate on how the gravitational waves are actually produced by this?
Yes. Well, it's going to be very easy. It's just going to be second order. So that means whenever you have a scalar perturbation, which I'm going to explain how that is being produced, you always have a second order production of gravitational wave just through gravitational interaction. Okay, so that's what happens. And this is, by the way, very standard. This is exactly what everyone who's studying primordial black holes does. They calculate the curvature perturbation or the effect of the ultra slow roll phase on the curvature perturbation, and then the gravitational waves are produced at second order. Okay, so it's technical, but it's nothing conceptually interesting is going on.
Just another question, just for clarification. So you're assuming the Cosmology is
yeah. For this, it's turned off, but so it's the rate is tiny for this kind of space. But
so this is assumptions on the shape of the potential.
Indeed. So let's say the potential is slightly the field space, the field range is slightly bigger than the range of the potential. So then Cosmology is negligible. But now we can also build potentials where Cosmology is the thing, and then the dynamics is slightly different. Instead of an entire volume going to the false vacuum, we have a bubble that propagates at the speed of light, reaching the Hubble sphere, and then freezing. But for all purposes, the only difference is that time of propagation, which is negligible compared to the rest of inflation. Okay, so that's basically it. So almost nothing changes in the story, nothing conceptual.
Provided the rate is smaller than Hubble.
Provided the rate is smaller, yeah. Provided the same thing is true for the Cosmology, but the point is, yeah, the caveat here, or let's say the weakness of this, is that it needs to be smaller than Hubble inflation. But as you will see, the strength of the gravitational wave signal is going to be proportional to this rate. So it cannot be much smaller. Okay, it can be smaller, but let's say an order or two of magnitude, but not much smaller. Otherwise, we don't get a signal. But it's just, I think it's an interesting parameter range to explore, and as you will see, the signals themselves are very interesting. Okay, so let me define one parameter that's going to control basically everything, and we call it gamma PT in the paper. Okay, and it's just given by this. So there's some numerical factor of around 1,000. Then gamma over V h to the 4. So this ratio, okay, h inflation, and delta V, this delta V. Okay, so the size of the energy difference compared to the energy in the inflaton field. So this will be half phi dot, where phi is the inflaton squared. Okay, so the kinetic energy of the inflaton, and all of this squared. Okay, so this basically will control the size of the curvature perturbation that's being produced and the gravitational waves, and it's very easy to understand. Basically, you need to produce some bubbles, so that's why it's proportional to gamma over VH to the 4. Then you need some energy in those bubbles, otherwise they don't do anything. And and this energy is produced gravitationally, so that's why this is squared. So you have delta V in this field compared to the inflaton energy. So that's going to be what the delta rho is. Okay, so this is going to control delta rho, and this is basically going to control how many of these bubbles. Okay, so number of bubbles. Okay, yeah, there was a question.
Why the inflated energy is given by its kinetic term?
Right. So that's a good question. It's basically similar to let me think about this. How do I want to explain this? Yeah. So the potential energy in the inflaton is responsible just for the inflation, but the kinetic energy of the inflaton is really the available energy that the inflaton has, and that's what you compare it to. I mean, also this is also true for the inflationary perturbations, right? The size of inflationary perturbations is Hubble over pi dot, and that's for a similar reason. But I will get to the equations, and you'll see this pop up there. Okay. So let me erase here. Good. So what happens? So we have, here's our inflationary volume. Like some Hubble volume went into this delta V, right? And we produce linear homogeneity that has to do with this size, okay? And basically the time at which this bubble is produced, that has to do with the frequency of the gravitational waves. But for complete phase transitions, that just happens at some point during inflation. There's a phase transition, and it ends. Okay, and you have produced a very specific frequency. Of course, there's some shape, but that shape is very well localized. Here, what happens is that the phase transition starts to occur after delta n, but it never completes. So you keep producing these bubbles throughout inflation until inflation ends. Okay, so what that means is basically you produce every frequency starting with some initial frequency that has to do with when this process started. Okay, so if you remember, the IR was lower frequencies, higher frequencies. Well, the earlier time of inflation was lower frequencies, the late time inflation was higher frequencies. So we're gonna have, so here's the Hubble sphere. Okay, this is 1 over AH, the Hubble sphere. So this is reheating, right? And we know we have some delta n. So here's delta n. We start at this point, okay? And we produce modes throughout inflation. And so we pick them up here, different redshifts after inflation. So we basically, it's almost like the state of fluctuations in the sense that you produce a very long range and you produce gravitational waves for almost any frequency, but starting with an initial frequency that's just set by the time at which the phase transition started. Okay, so what we expect is at the end of the day, and this is what we'll get. Let me just get there in a second. That if this is the frequency and this is omega gravitational wave, we'll have some initial frequency which is set here, and then we'll have some broad spectrum of perturbations and of gravitational waves, and essentially this is just set by delta n, and the height here, this is going to be set by this gamma pt, actually gamma pt squared. Okay, so this is what we expect, and let me just, through the rest of my talk, just explain quickly how do we calculate this, which is the long and annoying part in our paper, and we were stuck on this for some time. And this was done very beautifully by Yoel, and I implore you to read our appendix, which is pretty hard to read, but it's nice. It almost has no QFT, but it just has statistics of bubbles and how do we think about how do we think about how do we produce the spectrum out of this in gravitational waves? And I'm going to touch on this just barely, just to show you what we did. But for the rest of it, I really implore you to read the appendix. Of course, only if you like suffering.
Michael, can I ask you a question?
Yeah.
Are you also, so in this mechanism, you are also forming black holes? Right?
Indeed. So this is good. So this is what we want to do next, actually. So the primordial black hole production is very sensitive to the properties of the spectrum, essentially the non-Gaussian part of it, which is going to be very different here than what you get for the inflaton. And we do have some bound based on very rough estimates, just based on the regular story, but we do want to analyze this completely. So this is one of the follow-up projects that we're thinking about.
Sorry, can I ask one question?
Yeah.
So I think maybe you have already explained, but to get this flux spectrum, you assume that after phase transition, the region at the top of the potential just expand as it is. So no.
Well, yeah. So if here's your potential, okay, you basically you tunnel. The way Hawking-Moss works is that you tunnel to the top of the potential.
Yeah.
But of course, any small fluctuation will immediately take you down.
Right.
So you can think of it as you tunnel just slightly away from the top of the potential, and then you roll down here.
Mm-hmm.
So the difference is going to be this thing. Yeah.
So the bubble have a bubble patch size initially?
Yes, yeah. All the bubbles for Hawking-Moss are Hubble size, but that's true for almost any incomplete phase transition in the sense that eventually any bubble will reach the Hubble sphere. Okay, it just may happen after 1 year fold roughly. Okay, good. So let me talk about how do we get all of this. So of course, what we have here is a difference in the vacuum energy, so that changes rho and changes p. So we take a simplistic approach, which is already quite complicated, and we assume that the bubble wall energy is negligible, and most of the energy is just the delta V between the different vacua. And again, this is because the size of these bubbles is very large. Okay, and so in this case, the story is quite simplified. So the delta rho we have is basically just delta V. Okay, and now we can think of it as for any point. Okay, so this is delta rho of any point x. There's a delta V if that point is already within the bubble. Okay, and of course, just to normalize, we'll take it to minus delta rho if that bubble is before if that point is before the bubble reached there. So there's going to be some theta of t minus dx. Okay, so this is the Heaviside function. I think this is with minus sign, maybe plus sign, theta t minus an average of tx. Okay, so this is basically saying that the delta rho is just this delta V, but for any given point, that delta rho depends on whether the bubble reached this point or not. And of course, we average over different times of reaching any given point. So of course, this is independent of x. Okay, this is dependent on x in a specific realization, and this is what we get, and this affects the gravitational potential. Okay, through the continuity equation, we can think of this as delta rho or the Einstein equations. I mean, you can always change it whichever way you want. So this is the continuity equation, but you can get it also from the Einstein equations, and you find that this delta rho immediately affects the gravitational potential that you have defined. Okay, and at the end of the day, what we are going to compute is R, the curvature, or the gauge invariant curvature perturbation, which in this case is just going to be given by this. Okay, so this is minus h delta v over phi dot squared, and this is really where the delta v of phi dot squared picks up, times delta tx, where delta tx is just tx minus tx average. And as we see, at the end of the day, the whole story becomes the question of statistics of points and the times at which the bubbles reach them. Okay, so we have to now carefully take these statistics. Okay, so at the end of the day, we want to compute for a certain k, rk prime, and this will give us the power spectrum. Okay, this is how we define this power spectrum, but at the end of the day, we just have to take this, Fourier transform it. Yes, is the question?
Yes, this is the curvature outside the horizon for super horizon model.
Sorry?
This is the curvature, scalar curvature for super horizon model.
Yes, indeed.
But it seems to grow with time, which is at odds with what is commonly assumed. Usually, in the literature, that R is constant outside the.
Right. Good. So yeah. So this is a. We also have thought about this. So we think it's true. It's just based on the fact that you have different delta v's in different places. Okay, and it's a growth which is non-causal. Okay, but it just continues to grow. Indeed, outside the horizon. That growth is not important for a story. It changes the slope a little bit, but yeah, it is true that it does grow outside of the horizon.
But let's say you wait a very long time, then it becomes order 1. What does it mean? You will leave the perturbation regime.
Sure. Then you need to compute it again. I mean, you cannot use these equations anymore. Yeah. But yeah, that's a good question. But
so you expect this growth to stop at some point?
Yeah, I mean, I'm sorry. What growth? These are subdominant, and the delta V is small compared to to the dominating Hubble expansion. So this growth. I mean,
yeah, it's not going to affect any. For us, it's definitely not going to affect anything because inflation is not long, right? So it's not important, but it does affect the results somewhat. Okay, so we'll see that there's some slope at the end of the day to the spectrum, and this is because of this growth. But let me continue because
about 5 minutes.
Yeah, good. Okay, so at the end of the day, we see that what we need to compare is what we need to find is because R is the delta t proportional to delta t, which is the difference between bubble arriving at any given point compared with the average bubble arriving time for any given point. Okay, and what we need to do is find the 2-point function of this delta t, and for the gravitational wave, we need to find the 3 and the 4-point function of this delta t. Okay, so this is the hard part, and I'm not going to spend any time on this. Okay, so I'm just going to say that what we need at the end of the day is to find this delta tx prime. Okay, and we can use we can basically separate it into different regimes. So we can think about delta tx prime for when these 2 points are within. So given that you have one bubble between one bubble that contains them, that means they're within the Hubble volume of each other, and then of course that times the probability of this bubble containing them. And you can have the same thing when you have bubble that contains only x with this probability, and of course bubble containing only x prime and no bubbles at all. And what we find is that in the regime where gamma over v is less than Hubble to the 4th, this thing dominates. Okay, so we just need to ask ourselves, what is the probability of producing one bubble, and then the delta t x delta t x prime of assuming there's one bubble that contains them. And very, very quickly, what we find is that this we can express as an integral 0 to t s. Let me go quickly over this. So t minus t average squared times gamma over v times v overlap times dt. Okay, so the important thing is this gamma over v, as I said. So this is why in the strength of the perturbation has to do with gamma over v, and this v overlap is basically so this v overlap is a function of t. It's just the overlap volume of 2 bubble spheres originating at 2 different points, of 2 Hubble spheres originating at different points. So this is RH, so this is 1 over h, and let's say this is 1 over h, let me move this point closer, and this region is this overlap integral, and changes with time because the Hubble sphere shrinks with time. Okay, so this is at the end of the day what this whole calculation comes down to, and out of all of this, once putting all of this back into the power spectrum, we basically get that the power spectrum at the peak is equal to 10 to the 3 gamma pt, and the shape is given, as I said, by this, roughly, where, sorry, it goes down, wrong. So this behavior is due to the growth that we were describing. The points that entered earliest are largest, okay? But this is relatively flat. It's only like a log, if you want just a log growth. And this k is just given by 1 over h at the initial point, so at delta n e-folds, okay? And the size of this is this 10 to the 3 gamma pt. And this gamma pt, as I said, we can again, well, let me first calculate the gravitational wave because I don't have much time. Okay, so this is the power spectrum. Okay, it's important in its own, but we don't have a probe of the power spectrum at very high frequencies. The only thing we have is the gravitational waves, and these gravitational waves, let me calculate it here. So these gravitational waves are just produced. So the power spectrum of the gravitational waves is just du dv, some function of u and v, pr of pr of ku, pr ku. Okay, so this is of u. Okay, so we see this is secondary production of these gravitational waves. They're proportional to twice the power spectrum to times itself. So we can again talk about the omega gravitational wave that we get from this, and it's going to be, again, you can plot the numbers, around 100 gamma pt squared, which you can put in different ways. Okay, so let me put it this way, which is the worst for us. gamma over v h to the 4th squared times delta v over vb to the 4th power, okay? vb over h to the 4 to the 4th power, and the h at inflation compared to m Planck and 2 to the 5 10 to the minus 5, which is currently the bound on h at inflation. Okay, h everywhere is h inflation, and this is to the 8th power, and one more factor, 10 to the minus 3 epsilon slow roll to the 10 to the 4. Okay, so let me briefly go into what we get. So the way I put it here is very indicative. So it's the omega gravitational wave is a function of gamma over v h to the 4th squared. That's the rate of the phase transition, and then we can compare the delta v to v of the barrier. So if our potential had this height and this height as being equal, okay, then the signal is quite weak, okay, but it's extremely sensitive. It's extremely sensitive to the difference in this height. Okay, so even a factor of a few, which you can easily get with many different ways. Okay, already for this model will give you a gravitational wave spectrum which is quite large. So, Chava, if you allow me just 1 minute, I'm gonna just plot the gravitational wave spectrum in say what we're going to do next, which I already, I think, alluded to. Okay, so again, here's the entire spectrum. We have the CMB here, PPA here. Let's say this is Lisa and LIGO here. And there's going to be many new detectors in this range. Well, there are proposed many detectors in this range. Nobody knows if they're going to be built or not. And this is around, sorry, this is too much. This is around 10 to the minus 6, which is the area already excluded by n effective. Then the signals we have are here. Okay, so depending on the initial time of the space transition and the size of this delta v, we can get signals like this. Okay, as you can see, they're signals that can be seen by many different detectors across the entire range. Okay, and what's very interesting is that this height, the height of this, okay, is very dependent on the dynamics of inflation. If you remember, there was the v over phi dot, delta v over phi dot squared. So for instance, if you had a region of much slower roll or much faster roll, we would get a break here that's going to be dependent on the slow roll. Now, of course, this is also going to be dependent on gamma, on the production rate of these bubbles, and so that can also change. So basically, this change in the spectrum is going to be very sensitive to a combination of the phase transition rate and the tunneling rate and the slow roll parameter of the input.
If you see it in two different places, would you know that it's actually part of the same curve, or like you see it in Lisa and in pulse search? But you know, I mean, you say that you can have all kinds of features, yes? So would you know that this is actually?
Yeah, it's hard. The inverse problem, of course, is always hard. You don't know directly if it's the same thing, but you build more experiments, you see it across the entire range. You know that it's a region where it's excluded by CMB distortions. So if it is just the CMB, the inflationary Bessira production, then it implies something very strange for the slow roll parameter. And so that can happen. So it's either something weird going on with inflation that picks up the spectrum of the gravitational wave, or it's something like this. Okay. Of course, it's very hard to imagine you'll build more detectors and you see more gravitational waves at relatively the same height. But it's hard to explain this with phase transitions. Of course, it can always be some astrophysical noise, but given that we know how to measure these stochastic gravitational waves, this is, I think this is quite unique. Okay.
So there's something scaling variant going on in the early universe dynamics.
Exactly.
It's not trivial.
Right. And it's pretty hard to do it with the inflaton. You can do it with you can mimic this with the inflaton, but I think it's interesting that there's another possibility. Okay, so let me just briefly say what we're going to do next. Okay. So of course the part of the potential that is hardest to get is the fact that it starts quite late, because you need the coincidence that M is pretty close to Hubble, and it either doesn't get stuck or doesn't move very quickly. So that sort of needs a coincidence of scales. But it's very easy to imagine that you have a phase transition going on throughout inflation. Of course, you will not see it here in LISA or PTA, because everything is going to be the most sensitive thing is going to be the CMB itself. But it's very interesting to just analyze what are the CMB signals from such a phase transitions, and it's going to change the B mode spectra that you expect, and it's going to change the non-Gaussianity of the curvature perturbations themselves, the properties of the non-Gaussianity, and that's one thing we're going to study. And the second thing I already mentioned is for this mechanism, a very interesting question is what are the prospects of producing primordial black holes? And that, yeah, we don't know. So this is what we want to do next. And if you want, the primordial black holes limit, just by very crude estimate, is somewhere here. But again, this is highly sensitive because it's exponentially sensitive to the power of the power spectrum. Then it's going to be very sensitive to the non-Gaussian features of these bubble productions, and they are non-Gaussian, so we cannot say anything about them, which is not before we analyze this completely. Okay, so thank you.
One or two quick questions before we move on.
Yeah, sorry, but what's the amplitude of the power spectrum that you're getting out of this in order to have observable gravitational waves?
Right. So it's very dependent on the parameters. So if we have this again, here's the potential. It's literally this size and this size are the same. Okay, then we have a problem. The size is about 10 to the minus 8. But if we get even like 10 to the minus 18, sorry, but if we get like a factor of 100 between them, which is quite easy to get if you want, like one potential thing is some Z2 breaking potential that produces different heights of this and this. Okay, then you can be anywhere in the range of 10 to the minus 10, which is deep within the LISA range.
But what does this imply for the power spectrum of the perturbation? What's the amplitude of the power spectrum?
Good. So
let's fix the omega gravitational wave to 10 to the minus 10, so you want to see it at LISA. What does this imply for PR?
Good. So let's see. So this is, I can look at the paper. I think that's the easiest thing to do.
I understand what you're saying about non-Gaussianities, but if the amplitude that you're getting is very large, since you're getting an almost flat spectrum.
Yeah, so it's about 10 to the minus 3-ish. So it's not that large, okay? So if you want, the primordial black hole region is around 10 to the minus 2-ish, slightly above.
Okay.
But also it has scale that in any case you can't probe.
No, but you can probe by primordial black holes.
No, you see, because you will be producing, let's say, there are bubbles at any epoch that are collapsing in the early universe. In particular, you will form very light black holes that are extremely constrained by evaporation.
Yeah.
At some point, there is a bound on the fraction, which is of order 10 to the minus 10. I don't know.
Good. So the fraction. So the PR. That's if you believe the Gaussian. Just the Gaussian calculation.
I appreciate the caveat you're making.
Yeah. So if you believe the Gaussian calculation, so this is, if you want, this is around 10 to the minus 3 for the models we are looking for, and somewhere between 10 to the minus 1 or 2. We have looked at this. If you open our paper, we do have that line. So this is the primordial black hole exclusion. Okay, and this corresponds to this line would correspond then to 10 to the minus 10 size of omega gravitational wave, which is easily within the LISA range. Yeah.
Okay, thanks.
But nothing is special about this, right? We know that the thing that produces the right abundance of primordial black holes is around 10 to the minus 9. It gives signals around 10 to the minus 9 for LISA. Okay, so it doesn't surprise me that.
No, it's just that in that case, people assume that it's something peaked.
Indeed.
Whereas you have a flat, so
Indeed.
you will encounter the evaporation constraints at some point.
Right, but evaporation constraints are not different from overabundance of primordial black holes. So it's just different range, as you say, in frequency. But it's the same size, and since this is independent of scale, there's nothing interesting is going on.
So what do you mean it's the same size?
I mean,
it's not the same size. It's really, you cannot, at certain masses, you cannot have more than, let's say, 10 to the minus 7 of the dark matter in primordial black holes. And this corresponds to a very, very small.
Right, but it's exponentially sensitive to the power spectrum.
Yes.
So it doesn't change the bound. So then it's 10 to the minus 2 and not 10 to the minus 1. In the primordial, in the power spectrum.
Yeah, but it's very sensitive, as you were saying, to whether this Gaussian.
Indeed. That caveat, I completely agree. So that's something we want to calculate. But indeed, that may change the bound. We don't know which direction even. So yes. But anyway, it's not going to be much more than 10 to the minus 2, right? That's relatively where exponential factors should kick in.
But it's possible, I think, that once you take into account the non-Gaussianity, the line that you're drawing there above the one that you need to be seen, for example, at LISA, actually goes below.
Yeah, indeed. So that can happen. Yes, it's good. It can be sensitive, of course, because with non-Gaussian perturbations, you can get very large fluctuations without an exponential suppression, of course. I understand. I completely understand this. So that's why I said this is the next thing that we want to do.
All right, I think we need to move on. Let's thank Michael again.